Hi, in this video, I am introducing you to a new physics keyword called impulse. So this is an introduction to impulse. Impulse has a lot to do with momentum. They are not the same thing conceptually, but they are deeply related. And I'll show you how they're related in just a second. But first, let's talk about what impulse is on its own. So impulse is force acting over time. So it's force acting over time. In particular, if you're going to calculate the impulse, there is a formula, and this would be the impulse by a particular force. And the way you calculate it is the impulse is equal to, it's the force multiplied by the amount of time that the force is able to act, right? Some forces don't act forever, which is interesting. For example, when you push on a wall or a bowling ball or a baseball, your force only acts for a short amount of time. As an alternative, a force that acts for very, very long periods of time is forces like the support force. For example, if you're standing on a floor or sitting on a chair for a long period of time, let's say you're working on your homework and you're sitting in a chair, that chair is pushing up on your body with a supporting force, say over the course of 1 full hour, right? Gravity is also supplying a force known as the weight force, which over your lifetime never turns off, right? An object's weight doesn't turn off as long as they sort of stay nearby the earth. Okay, so impulse is force times time. So as an example of calculating an impulse, let's do this. So it's a simple equation. You have two sort of values that are different. One is a force of a strength of 4 newtons towards the right. So forces are vectors, right? So you have to describe both how strong or how much that vector is, as well as in which direction. In this case, the strength of the force is 4 newtons, and the direction of that force is that little right arrow. So let me erase those little orange marks. That's the force. And this right here is the amount of time that I'm saying that force acts for. So this 4 Newton force towards the right acts for 3 seconds. So if I'm going to calculate this, what I'll do is, it's pretty simple, right? You just put in 4 newtons towards the right and you multiply by 3 seconds. And the answer to that is 4 times 3 is 12. And the units are newtons and seconds. Newtons times the second, right? Because we took a force and multiplied by time. And this impulse that we just calculated is a vector. And the result is towards the right because the force was towards the right. So this is the impulse. That's impulse number 1. I'm going to say that there is another impulse by a different force acting for a different amount of time. Impulse number 2, if we calculate it, it's 12 newtons, so it's a stronger force acting towards the right, and it only acts for 1 second. It doesn't get to act for very long, but it is stronger. And you can see that this actually calculates out to the very same amount of impulse, including the direction. The direction is also towards the right. All right, so up here I said that impulse, which is force times time, is related to momentum, right? It's related to this other concept. And now I'm going to describe how it's related to that concept. here is the rule. The rule is this. So this is a piece of physics right here. A force acting for a certain amount of time, actually, let me take it back. In particular, it's the net force on an object acting for a certain amount of time. So it's the impulse by the net force results in changing the momentum of the object where that net force is acting. So the impulse changes momentum. So impulse units are these newtons times seconds units, right? Newtons times seconds for these two impulses that we calculated. And that impulse actually is also momentum units, kilograms, meters per second, right? Remember, momentum is mass times velocity. So that means that the units of momentum will be the units of mass times the units of velocity. So kilograms times meters per second. And it turns out that the Newton times the second is equal to the kilogram meter per second. This statement right here is physics. It's a relationship between a force acting for a certain amount of time and this causing momentum change, right? Sorry to do this. Momentum change, right? Physics is all about trying to figure out how to cause nature to be different, right? So how do you change an object's momentum? Well, you need to change that object's velocity somehow, right? You need to change that object's motion. And the way that you change motion is you use a net force. And if you use the net force for a longer amount of time, that will result in a larger change in momentum. And if you use the net force for a very, very short amount of time, then that will amount to not very much change in momentum. I hope that makes some sense. But this is called the impulse momentum theorem. And the impulse momentum theorem is the impulse by the net force is the change in the momentum. It's the only reason that momentum can change. So physicists would be able to show you this really quickly, but it's a slight set of math choices or a little bit of algebra. But if you were comfortable with algebra, I bet you it wouldn't be too much of a leap for you to take Newton's second law and turn it into the momentum impulse theorem. It's actually the same thing. The impulse momentum theorem is just a restatement. It's a different form of Newton's second law. And if you'll recall, Newton's second law says that the acceleration is equal to the net force acting on an object divided by that object's inertia, right? Divided by that object's mass. So acceleration tells me how the motion of an object is going to change, right? That's what acceleration describes. Acceleration describes how quickly an object's motion is changing. The way you cause this acceleration is by applying a net force. And you can kind of see that the impulse momentum theorem is saying the same thing. If a net force is applied for a longer amount of time, then that means that the object will be able to accelerate for a longer amount of time, which ultimately results in a larger change in the velocity, right? A larger change in the motion, which also means a larger change in that object's momentum, right? So they really do say the same thing. So let's do an example. So the example looks like this. I have an object. Here it is. It's a box. And we're going to start off by saying that the object has 0 momentum to start with. And we're going to say that it's on a nice flat floor. and there is no friction. So as you see it, our object has no momentum, right? The momentum is equal to 0. This object has no reason to speed up or slow down in any direction or gain any motion. So there is no reason for its momentum to change. Not yet, anyways. But what we're going to do now is we're going to apply an impulse. So we're going to apply impulse number 1. Impulse number 1 is this impulse. It's 12 Newton seconds towards the right. And so the way that we apply that particular impulse is for 3 seconds, we're going to make sure that the net force on our object is 4 newtons towards the right. So let's do that. 3 seconds, 4 newtons to the right. So here is 4 newtons to the right. And we're going to apply that force for 3 seconds. So once we apply impulse number 1, we get a change in momentum is equal to the impulse. In this case, it's impulse number 1. And that value is 12 newtons seconds towards the right. But I told you up here that a Newton second is the same units as momentum units, kilograms meters per second. So the change in momentum is actually equal to 12 kilograms meters per second towards the right. But I want you to be very careful. This is the change in the momentum. So the way you think about change is you have a starting value and a finishing value. And the starting value in our case is our object starts at rest, so the starting value is 0. The finishing value is this much change from 0. And if you add this much to 0, the finishing value is, it happens to have the same value as the change itself. So the finishing value is 12 kilograms meters per second towards the right. Okay, so now let's apply impulse number 2. So impulse number 2 is this stronger force acting for a smaller amount of time, right? Impulse number 2. But it turned out to be the very same impulse. So what that's going to look like is our box will be over here. It's got that mass m. We don't know the mass, but it has some momentum. So I'm going to draw these little motion lines. And now we're going to apply 12 newtons of force, a much stronger force towards the right, but we're going to only apply it for 1 second. But we're applying this impulse on an object that's already moving. So this impulse is merely only going to increase the momentum. So let's play the same game. Let's apply impulse number 2. The starting value is the value of the momentum actually after impulse 1, right? So the starting value is this value, 12 kilograms meters per second towards the right. And the finishing value is the result of adding impulse number 2 to the starting value, because impulse number 2 is the change. So the change causes the finishing value to have this large value of 24 kilograms meters per second towards the right. So the result of applying impulse 1 first and then impulse 2 afterwards is to increase the momentum of our object from 0 all the way to 24 towards the right. So now I'm going to sneak in another impulse. Oops. Let's say that there is an impulse number 3. And the details of this impulse is we're going to use a 50 Newton leftwards force, and we're only going to use it for 1/2 of a second, right? So the result of using impulse number 3, right, which has this data, the result is, so let's calculate it, impulse 3 equals 50 newtons towards the left times 1/2 a second. This is 25 newtons seconds towards the left. But you know that the newton times the second, which is the impulse unit, is actually the same thing as the momentum unit, because impulse changes momentum. So this can also be read as 25 kilograms meters per second towards the left. So let me draw a picture of what we have. We have a box who's actually moving quite fast towards the right because it has 24 kilograms meters per second towards the right worth of momentum. But now there is a 50 Newton force that acts towards the left for this 1/2 of a second time duration. So, let's apply that force. Here it is, really big force acting for a very short amount of time. And this is the change, right? Because that's what the impulse momentum theorem says. So impulse 3 is going to cause the momentum of our object to change by this amount. So this is very strange. In a sense, this 24 kilograms meters per second towards the right is kind of a positive value. Whereas this change, you see the leftward arrow, is kind of a negative change. So what this looks like is it looks like 24 with a minus sign, with a plus sign, and we are going to change that value. That is, we're going to add something that is negative. We're going to change it by negative 25. And can you see that this equals -1? Or in the language of our momentum, we have an object that after all 3 impulses have acted on the object, the result is our object is moving very slowly with a small momentum towards the left. Do you see that? This is a leftward momentum. This is what it looks like when you think of things bouncing, right? The momentum used to be towards the right. Then there was a fairly large impulse in the opposite direction. And that results in not just stopping the object, but actually stopping it and then pushing it out backwards, right? That's what a bounce is. That's what reflections look like, right? When a ball bounces off a wall, you can see that that is a large change in momentum because you're changing the momentum, say, from a positive value to a negative value, right? And that often requires a very large impulse. And in order to get a large impulse, often that means you're using a very large force. And large force can be damaging, but it can also be very useful, right? You can engineer situations where bouncing is part of the engineering because that's a transference of a very large amount of momentum.